Okay, so we've talked about classifications of matter. We've talked about units and derived units of measurement. Now we need to talk about some important details when it comes to actually making measurements. And that is first that whenever we make a measurement in the laboratory or outside in the world, there's always some uncertainty associated with that measurement. We can talk about that uncertainty in a couple different ways, and we'll go into some more details in the following slides, but we can talk about it specifically in terms of its precision and its accuracy for a measurement or a group of measurements. This is best illustrated using kind of a cartoon example where we have a dartboard and we throw 3 darts at the board. We can illustrate accuracy based off of the bullseye being the true value, what we're trying to attend or achieve, but precision is how closely grouped those 3 darts are. So in this first example on the left, we see a case where we've got poor precision and poor accuracy. Poor accuracy because all 3 of the darts are far away from the bullseye. Poor precision because all 3 of the darts are also far away from each other. They're not closely grouped. And so we would have no real idea, say we threw a 4th dart, we would have really no idea where that 4th dart was going to land because we have poor precision. The middle example is the case where we have good precision. There are all 3 of those darts closely grouped together, and we have poor accuracy because the darts are still far away from the bullseye. But if we threw a 4th dart at the board and assumed that, we have the same kind of level of, if we did everything the same as previously, we would have a good idea where that dart was going to land, but it is still unfortunately far away from the bullseye. Now, the ideal case in measurement is where we have both good precision, so close grouping of our measurements, and also good accuracy, close to the true value. Let's make this practical by going through one specific example. Let's say we had 3 students, Lubika, Stephanie, and John, who are in the lab measuring the density of a gold block. And we know that density of gold is 19.32 grams per centimeter cubed, as reported. And in this first trial, Lubika, Stephanie, and John took 3 measurements. And what we see is that in the first trial, we have poor precision. There's a large range of measurements. It ranges all the way from about 18.5 almost up to 20. And additionally, none of the students' individual measurements are close to the accepted value. Now, their average together is moderately close. So we would have a moderate average accuracy, but the precision is poor. In trial 2, what we see is that they were more careful and they got 3 very close measurements for the density. Unfortunately, their values are not close to the accepted value. So we have good precision here, but poor accuracy. And then in the last trial is a case where we now attain the good accuracy and good precision. Their measurements are all closely grouped together, that's precision. And those measurements and the average measurement is close to the accepted value. That's good accuracy. Now, additionally, when we are talking about uncertainty, it also shows up in how we actually measure on a physical tool. So any tool of measurement that has markings, there will be some level of uncertainty associated with that tool. So in this case, a thermometer that has markings at 25 and 30, and you can see the level lies somewhere in between those two. We have to estimate that last digit. And so we would estimate it to be approximately 27 degrees Celsius. And that last digit then would be our uncertain digit because it's the one that falls in between the smallest markings. Now, if my markings are close together, so if the markings were at 25 and 26 and the value and the liquid level was in between those two, if my markings are close together, I can estimate one additional digit between those 2 markings. So if the markings are every 1, I should be able to estimate to at least 0.5. In this case, my markings are not that close together. They're not every 1, they're every 5. And so as a result, I can't really estimate an additional digit. I can't say it's 27.5. I can really only estimate to the ones place in this case because my markings are not every 1, but every 5. And the same thing would be true if it was every 10. If it was a 20 and 30, the most I could estimate would be the ones digit. If markings were every 100, then maybe I would only be able to estimate to the tens place. If my markings are every 0.1, then I should be able to estimate to the 0.05 markings. But the important thing to remember is that the last digit of every measurement is an estimate and is therefore has some level of uncertainty associated with it. And that becomes very important when it comes to doing calculations. If we're calculating the size of a beam that we need for a bridge, we're going to have some multiplication or addition involved in some kind of calculation. And each time we do calculations, that could then propagate the uncertainty from each of the measurements that are involved. And so we have to keep track of those. And the way that we do that is we use something known as significant figures. This keeps track of the level of precision or uncertainty in measurements and in calculations. So there are some rules for significant figures. First, all non-zero values are significant. So that's very straightforward. Any number that's in any reported measurement that has a non-zero value, that non-zero value is significant. Zeros at the beginning of a number, at the very beginning of a number, so if we have 0.00005, all those zeros at the beginning of the number are never significant. Zeros in between non-zero numbers are significant always. So if we have 1001, we would have 1001. Those two zeros in between the two non-zero numbers are always significant. And then zeros at the end of a number are significant if the number contains a decimal point. So if we have a decimal point, something like, say, 100.05 or 100.000, because I have the decimal point there, all of those zeros are significant. Let's go through another way of helping to remember these. Really, the non-zero numbers, those are fairly easy to say, yeah, those are significant, but the zeros always get a little confusing. So here's an alternative way of keeping track of significant figures, especially when there's zeros involved. And it comes from this kind of graphic example here, where we have the map of the United States. We all know where the Pacific Ocean and the Atlantic Ocean are. And so bear with me as we use this example. If a period is present, then we start at the Pacific and we work right until we hit the first non-zero number. So what do I mean here? Period is another term for a decimal point. So if a period or a decimal point is present, then I take the number that's given, I will start at the left and I will work my way right until I hit the first non-zero number. So nothing is significant until I hit the first non-zero number. Nothing is significant until I hit the first non-zero number, and then everything is significant after that. So here's some examples. 0.0002154. There is a period present, so I start at the Pacific, the left, I work my way right. The first zero, that's not significant. Second zero is not significant. Third zero is not significant. Fourth zero is not significant. Nothing is significant until I hit the first non-zero digit, so 2. And then everything after that is significant. So 0.0002154 has 4 significant figures. 5100.0, on the other hand, it has a period present. I start at the left, I start at the Pacific, work my way right, and turns out the very first number is a non-zero number, so all of the numbers are significant, and I have 5 significant figures. Same for 2.100, that one has 4 significant figures. So this is the case where I have a period or a decimal point present. If the period is absent, then I start at the Atlantic Ocean and I work left until I hit the first non-zero number. So again, nothing is significant until you hit the first non-zero number, and then everything is significant after that. Examples for this, say some ginormous number like 1,540,000,000. So we're talking about 1,540,000,000. There's no period or no decimal point, so I start at the Atlantic, the right, and I work my way left until I hit the first non-zero digit. So none of those zeros are significant. The 4 is the first significant digit, and then the 5 and the 1. So this has 3 significant figures. Same with this other large number here. In this case, 214,010,000,000 has 5 significant digits because there's no period. None of the leading zeros are significant. The 1 is the first significant digit. Then everything after that, including the 0, is significant. And then lastly, again, we can have this, astronomically large number, but we can systematically go through and determine what numbers are significant and hence what numbers we can rely on, whereas what numbers are significant. The very first significant digit, or the number to the farthest to the right that is significant, that is the uncertain digit. As everything after that, we don't rely on at all, but that one is the estimated digit. Okay, so what does this look like when we try to keep track of uncertainty or precision in calculations? Well, there's a couple different rules. Let's take this example here where we have addition and subtraction. Here we're just doing addition. 20.42 plus 1.3222 plus 83.1. And we add those all up, we would come out with 104.842. But which digit in that final sum is uncertain? In the first number, the 2 at the hundredth place was uncertain. It's my estimated digit. For 1.322, it's the thousandth place, and for 83.1, it's the 10th place. So which digit is uncertain? Well, in addition and subtraction, the result has the same number of decimal places as the measurement with the fewest decimal places. So one of these numbers has an uncertainty in the 10th place. So my final number has to have uncertainty in the 10th place. So here, I would just end up with rounding just to the 10th place. Now there is a quick note here with rounding in case you're unfamiliar. For rounding, if the first digit after the uncertain digit is less than 5, we just remove those digits and leave the uncertain digit unchanged. So in this case above here, the uncertain digit is the 8. The number coming right after that is a 4. That is less than 5. And so I just drop the 4 and the 2 to leave me 104.8. If, however, the first digit after the uncertain digit is 5 or greater, then I will round up. I'll remove those other digits, but I'll increase the uncertain digit by 1. So if it was 104.862, then I would round it to 104.9. All right, what about cases of multiplication and division? So let's say I had 20.41 times 3.2. I just multiply that out and my calculator will say, oh, the answer is 65.312, but where in this case is the uncertain digit? Well, for multiplication and division, the result has to have the same number of significant figures as the measurement with the least number of significant figures. This is different from addition and subtraction. So in this case, 3.2 has only 2 significant figures, whereas 20.41 has 4 significant figures. My final answer has to have the same number as the least number of significant figures, so it can only have 2. I have to round to 65. This might be a little confusing. Why is that the case compared to the addition and subtraction? Why does multiplication and division depend on the number of significant figures? Well, let's take an example for this. Let's take 1.5 times 100.5. And remember that the last digit is the uncertain digit. It's the estimated digit. So let's take this case here, and for illustration case, let's take the widest uncertainty possible. So since that's the estimated digit, let's say that it's possible that that last digit for the first case could be anywhere between 0 and 9. And same for the last digit of the 100.5. So my possibilities are I could range anywhere from 1.0 all the way up to 1.9 because that last digit is estimated. And for 100.5, that really could be anywhere between 100.0 and 100.9. Now, if I take the widest uncertainties, let's find the largest and smallest possibilities based off of these uncertainties. So the smallest or the largest is if I take 1.9 times 100.9. That gets me 191.71. If I take the smallest, that's 1.0 times 100.0, that just gets me 100.0. Now, if I compare these two values, what I see is that the uncertainty comes in the tens place here. The uncertainty is in the tens place because in one case I have 191.7 and in the other case I have just 100. So the first place of change is that at that tens place. And so I'm really, the uncertain digit is the tens place digit. And so I can only have two, I only have one certain digit, that's the 1, and then one estimated digit. That would be, in this case, the 9 or the 0. And so I can see that in this case, I am limited only to 2 significant figures as predicted by the rule.